welcome to the Deep Dive. Today we're looking at something really pushing the limits. It's high-speed milling of aluminum.
Yeah, it sounds simple, just cutting metal fast, but it's way more than that.
It really is. We're going to dig into how tool manufacturers are basically fighting physics at extreme speeds. It's less about just spinning tools fast and more about this, constant engineering battle against centrifugal force.
Exactly. It's a real fight against inertia. When we talk high-speed milling or HSM, we're not talking just a little faster. Cutting speeds can be, 1.5 to maybe 4 times higher than standard.
4 times?
Yeah, and that often means rotational speeds hitting 30,000 RPM, sometimes even higher. The whole point is efficiency, really. Getting lots of material removed quickly, but you also need incredibly high accuracy and a perfect surface finish.
Okay, so why aluminum? What is it about aluminum that requires these, extreme measures?
Well, aluminum's light, right? So you can remove a lot of it very fast, which is great for productivity. That's the big economic driver.
Makes sense.
But it's also quite soft, and often you need this mirror-like surface finish, so any instability from those huge rotational forces, any tiny vibration or wobble, it just gets magnified instantly in the final part.
Ah, I see.
So yeah, the goal is efficient removal, absolutely, but it has to be coupled with super high accuracy and a flawless finish.
So our mission today is to unpack that conflict. What are the big engineering hurdles trying to basically tear the tool apart? And maybe more importantly, what are the clever solutions keeping these cutters together and cutting precisely under all that stress?
Okay, let's start with the biggest problem.
Balance.
When you're machining at these incredibly high rotational speeds, you get substantial centrifugal loads acting on every single part of that milling tool.
Right, everything wants to fly outwards.
Exactly. And this constant outward force is the primary threat to the tool's balance. If you lose that balance, even a tiny bit, you could face immediate catastrophic failure, or at the very least, terrible chatter marks that ruin the workpiece.
So spinning at, say, 30,000 RPM, you can't just balance the tool after it's made and call it good, can you?
No, not really, or not reliably enough. That's why the industry has moved towards this idea of balance by design.
Balance by design.
Yeah.
Okay, what does that mean in practice?
It means that before any metal is even cut for the tool itself, way back in the 3D modeling, the CAD stage, engineers design the tool structure so its mass distribution is theoretically perfectly symmetric around the tool's axis.
Huh. Let's pause on that for a second. If they design it perfectly symmetrically in the computer, why do they still need to do physical balancing later? Is the design not perfect?
Well, the design is the ideal starting point.
Yeah.
But the engineered balance, the virtual one, it's really about minimizing the inherent errors that creep in during manufacturing. Tiny tolerances, slight variations in the material density.
Got it. Little real-world imperfections.
Precisely. So this design approach drastically reduces that residual imbalance. Think of it like starting a race, maybe 90% of the way to the finish line already. It makes the physical balancing you still have to do much quicker, easier, and critically much more reliable. You're just correcting tiny deviations, not wrestling with a fundamentally unbalanced design.
That makes a lot of sense.
Yeah.
Okay, before we get into the nitty-gritty engineering, let's categorize the tools themselves. What are the main types of cutters we're actually talking about in this super high-speed world?
We generally see 3 main types. First, you have indexable tools. These are the ones assembled from multiple pieces, a tool body, and then inserts you can swap out.
Right, the ones with the little cutting tips.
Yeah. Then second, you have solid cutters. These are usually solid carbide end mills, just one piece of very hard material.
Okay.
And third, there are ISCAR assembled tools.
SC. Remind me what that stands for.
Solid carbide exchangeable module. Basically, they use replaceable carbide cutting heads that screw or clamp onto a reusable shank, kind of a hybrid approach.
What's interesting there is the difference in, complexity for balancing. The solid tools and those SM heads, they're pretty much monolithic, right? One piece.
Essentially, yes.
So achieving that balance by design structure must be, simpler.
Relatively speaking, yes, much simpler. But the indexable tools, the ones built from multiple bits and pieces, they're the real headache for high speed, aren't they?
Oh, absolutely. They face the most critical HSM requirements, hands down. Every single insert, every little clamping screw, the shape of every chip gullet, each one adds a potential point where mass could be slightly off-center. It's the multi-part tool that really pushes the engineering limits.
Okay, so let's focus right there then. Indexable tools, milling aluminum at crazy speeds. If stopping those inserts from, becoming tiny projectiles is priority number 1, what are the key engineering demands? the non-negotiables.
First and foremost, you absolutely have to prevent radial displacement of the inserts. Those centrifugal forces are enormous, and if the insert moves even slightly outward, it's game over. So secure clamping is paramount.
Right. Anchor them down hard. Exactly. Second, you need to minimize the mass of every component. Lighter inserts, lighter screws, lighter tool body where possible. Less mass means less centrifugal load trying to pull it apart. Simple physics, but hard to implement.
And beyond just holding it together, what about the actual cutting? Does the geometry change much for high speed?
Yes, significantly. The tool needs a very light, easy cutting action. This is crucial, especially if you're using long-reach tools where any vibration gets amplified by the leverage.
Okay, light cutting.
And then there's chip evacuation. You're removing so much material so fast. So the chip gullets, the channels the chips fly out through need to be optimized. You need maximum space for chips to get out cleanly, but without compromising the core strength of the tool body itself. It's a balancing act.
Strength versus space. Got it. Now, to see this in the real world, our sources mention manufacturers like ISCAR categorizing their indexable aluminum tools. They seem to put them into 3 performance groups based on speed capability.
That's right. And looking at those groups and the speeds they handle really illustrates how the engineering solutions have to evolve.
Okay, let's break that down. Group 1.
Group 1 are the multi-purpose tools, sort of the general duty cutters. They're versatile, used on various non-ferrous metals, not just aluminum. Speed-wise, they operate up to about 1,000 meters per minute.
Which is roughly?
About 3,280 surface feet per minute, or SFM. For these, they often use the same basic insert shape, but just tweak the geometry, the rake, and relief faces for different materials or applications.
Okay, standard stuff,
Yeah.
relatively speaking. Then there's the middle group.
Yep, the prolific tools.
Yeah.
These were developed more specifically for intensive operations, like heavy ramp-down milling passes. They push the speed up to 2,000 meters per minute.
Double the speed. That's 65-60 SFM. Getting pretty fast.
It is. And that speed is generally achievable with, let's say, enhanced but still somewhat conventional insert retention methods.
But then there's the top tier, Group 3, the high-efficiency HSM cutters. You said 2,000 millimins was fast? What kind of speeds are we talking about at the extreme end here?
This is where things get really serious. These tools are engineered for extremely high cutting speeds. We're talking up to 5,000 meters per minute.
5,000, that's what, 16,400 SFM? That's insane speed for a cutting tool.
It really is. Think about the forces involved. And the absolute key feature, the thing that enables this massive leap in performance, is a specialized insert retention mechanism. It's not just about clamping tight anymore. You need a positive lock to physically stop that radial displacement from the massive centrifugal forces.
A lock, not just a clamp. Okay, that makes sense. So once you've tackled the physics of spinning that fast with clever design and locking mechanisms, the focus must shift to, like, long-term reliability, right? Maintenance.
Absolutely. We talked about the forces on the inserts, but think about the tiny clamping screws holding them. They take a beating.
Yeah, I bet.
Which leads to some pretty strict maintenance guidelines. For many standard HSM tools, ISCAR, for instance, recommends replacing the clamping screw after every 10 times you replace the insert it holds.
10 times. That seems frequent, but okay, fatigue point.
It's a critical fatigue point, yeah. But I understand for some of the most aggressive, specialized, ultra-high-speed tools, that rule gets even stricter.
Oh, how so?
Well, in some of those very high-end HSM tool designs, the screws are actually packaged with the inserts. They're selected as a matched set, often weighed or measured within extremely tight tolerances to meet the necessary overall balance grade for the assembled cutter.
Wow, matched sets.
Yeah. And if you're using those precision matched sets, the rule becomes replace the screw every single time you replace the insert. You just can't risk reusing a screw that might be slightly worn or different because that tiny change could throw off the balance enough to cause problems at 5,000 meters per minute.
That level of precision is just incredible. And it highlights something important. It's not just the cutter itself, it's the whole system, right?
Exactly. If you look at the broader picture, there's an ISO standard, ISO 16084, that basically formalizes this. It states that the balancing requirements apply to the entire tooling system, meaning the tool assembly itself, plus the basic adapter holding it in the machine spindle, and any intermediate bits like extensions or reducers. The whole stack needs to meet that stringent balance grade.
So a shop can't just buy a perfectly balanced cutter head and stick it on some old, maybe slightly worn extension tool and expect it to work at top speed.
Nope. The weakest link breaks the chain, essentially. The entire system has to be certified and maintained to that high standard. It definitely increases the complexity of tool management.
It really forces a systems approach, doesn't it?
Okay.
Let's pivot a bit to some of the cool new tech. What innovations are pushing the boundaries, maybe even for those Group 1 and 2 tools?
Well, even in the general duty space, we're seeing improvements. For instance, new round inserts, specifically for non-ferrous metals like aluminum, often feature a polished top face. That's the rake face.
Polished. Why polish the cutting face? What does that do at these speeds?
Good question. The rake face is where the chip slides right after it's sheared off. Polishing that surface dramatically reduces friction. This improves how the chip flows away, and crucially, it helps eliminate a really common problem called built-up edge, or BUE.
Built-up edge?
Yeah.
Where the aluminum sort of welds itself to the tool.
Exactly that. It sticks to the cutting edge, ruins the surface finish on the part, increases cutting forces, and shortens tool life. So polishing the rake face helps prevent that, leading to better finishes and longer-lasting inserts.
Interesting. And these newer round inserts, they come in different flavors, right?
Yeah, typically two main geometries. There's a plain edge, usually for semi-finishing where you want a smooth cut, and then there's a serrated edge.
Serrated, like little teeth. What's that for?
Right. The serrated edge is more for roughing, getting a lot of material off quickly. It's also really good for situations that aren't perfectly stable. Maybe you have a really long tool hanging out, long reach, or you're cutting a thin-walled part that might vibrate. The serrations help break up the chip and improve stability.
Okay. And beyond the insert edge itself, what about getting coolant to the cut? That must be tricky with everything spinning so fast and generating effectively its own wind.
Oh yeah, coolant delivery is critical. There's been a lot of work there. New end mill heads, especially those using advanced connections like Multimaster or FlexFit, have really benefited from computational fluid dynamics CFD modeling.
Using computers to model the fluid flow.
Exactly. They use CFD to redesign the internal coolant channels inside the tool body and head. The goal is usually twofold. Maximize the coolant flow rate getting to the cutting edge while also minimizing the pressure drop needed to get it there, making sure high-pressure coolant spray is exactly where it's needed most, even against those centrifugal forces.
That's some detailed engineering. Now let's jump back to the really high speeds, groups 2 and 3. You mentioned the big deal was those anti-movement locking mechanisms for the inserts. What's the latest development showing they're still pushing things there?
Well, a recent focus has been enabling these high-security, high-speed tool bodies to accept larger inserts.
Larger inserts? Isn't that counterintuitive? I thought minimizing mass was key.
It is, but they've found ways to securely hold larger inserts now. And the advantage is significant. Larger inserts mean you can take much deeper cuts. We're talking depths of cut up to maybe 22 millimeters now in some cases.
Wow, nearly an inch deep at those speeds.
Yeah. It means you can really utilize the power of modern high-horsepower machine tools much more effectively. So it's kind of an engineering win getting bigger and faster securely.
Okay, and the newest, maybe most aggressive innovation mentioned in our sources, this 14 millimeter serrated insert for existing high-speed cutters. That sounds like it combines a few things we've talked about.
It really does. It's designed as a productivity booster. It has that polished rake face we discussed for good ship flow. It has a super positive cutting geometry for that light cutting action. And it has those sharp serrated cutting edges.
And the serrations you said are for stability and roughing.
Yes, but here their primary job is a very deliberate chip splitting action.
Chip splitting. Explain that.
Okay. When you take a wide cut, you can generate a really wide chip, which can be hard to manage and evacuate. The serrations intentionally break that wide chip into multiple, smaller, narrower segments as it's being formed.
Okay, like pre-chopping the chip.
Pretty much. And this solves several problems at once. First, smaller chips are much easier to evacuate from the cutting zone. Second, it reduces the risk of chips getting jammed or recut. Third, it significantly improves the tool's dynamic stability, less vibration at high RPMs. And the big payoff. Because it's more stable and evacuation is better, you can often push the feed rate higher, really boosting productivity, especially in rough milling.
That's clever. A multitasking cutting edge. Finally, we shouldn't forget the solid tools, the end mills, and the ISCAR heads. Are they seeing similar kinds of advancements for stability?
They definitely are. Stability is key across the board. One important innovation for solid carbide tools and exchangeable heads is the use of variable fluid helix angles.
Variable helix.
Right.
So the spiral grooves aren't all at the same angle.
Correct. For example, you might have a 4-flute tool where each flute has a slightly different helix angle, maybe 35 degrees on one, 38 on the next, and so on. This variation disrupts the regular pattern of cutting forces and helps break up harmonic vibrations.
So it's like acoustic engineering applied to milling.
That's a great way to put it. It significantly improves the dynamic stability across a really wide range of operations, from heavy roughing cuts all the way to fine finishing passes.
So wrapping this up, what's the big picture here? It feels like machine tools themselves keep getting faster, capable of higher speeds and feeds, but maybe the cutting tools is often the real bottleneck.
That's often the case. The takeaway is that ultra-high-speed milling of aluminum isn't some niche thing anymore. It's becoming a standard approach for high productivity. But this puts immense and constantly evolving demands on cutting tool design. It requires this nonstop innovation cycle focused on balancing the entire system, perfecting how inserts are held, and managing chips that are flying away at incredible velocities.
It's a fascinating engineering race. And considering we talked about needing specialized locks just to handle 5,000 meters per minute reliably, here's something for you listening to think about. What comes next? What currently unseen design solutions, maybe active damping systems built into the tool, or using exotic new materials will be needed to safely and reliably push cutting speeds 5 times higher than even today's extremes? The engineers keep pushing the limits, forcing physics to keep up.